I do want to make this class interesting for you, and I'm going to try and do my best. We covered the syllabus last time, right? And now what we want to do is get a bit into chapter one and also talk a little bit about what geologists do. Let's start off with a little video here. This is a geologist, and she's talking about what you can do with a degree in geology. We'll start off with that.
My name is Cindy Gothberg. I'm a geologist at TerraTech, a Schlumberger company. As a petrologist, I look at sediments from all over the world: Australia, Africa, Europe, Canada, and of course the United States. Because I look at such diverse basins, I've actually gone to these locations. When I travel for work, I'm usually presenting at conferences or doing microscope work or core descriptions. Through the microscope work, we're able to identify the zones of interest for our clients. After I graduated high school, I was working some entry-level jobs, working nights, serving, and I just wanted to get a degree so I wouldn't spend the rest of my life working two jobs. I remember one day getting in trouble for leaving work 15 minutes early, and I just thought, there's got to be a better way to make it through life. My degree is in Applied Environmental Geoscience from Weber State University. I chose Weber State because the tuition is very affordable. I decided to go into the geosciences because I wanted a degree where I could make a difference, help the environment. I really like the outdoors, hiking around, and I wanted something where I could still be active. There was a lot of availability from my professors. We would go camping and they would just share all of their knowledge about the central Utah and southern Utah geology. There was a lot of applied learning, hands-on problems, where the homework assignments are geared towards real-life work situations. I was able to incorporate things I learned from my professors on field trips and use it for field courses that I take clients on now. We work with clients from Saudi Arabia, Australia, Europe, South America, and I'm able to show them the beautiful Utah geology. So my first job out of college was environmental work, where I went to different Superfund sites and did cleanup restorations. Examples include Hurricane Katrina, oil spill, or some sort of ground contamination. We'd go to the site, usually working 12 to 16 hours a day, not stop until the remediation was complete. After doing that job for a few years and always being on the road, going from one natural disaster to another, although it was rewarding, I couldn't do it anymore. I needed a job that was a little more stable with a 9 to 5 hours, so that's where I came to TerraTech. Going forward, I have the opportunity to travel a lot with this job and to relocate. We have offices all over the world, in South America, Africa, Europe, Australia, so eventually I see myself going anywhere. For anyone who's hesitating on coming back to school, just think of it as one semester at a time. Once you start, you can realize that it's actually very achievable. You'll make friends, be able to have study groups with people, and get through it. The most important part is to get started.
I hope that helped you get an idea as to what geologists do. To make a long story short, um, geologists can be involved in working in all sorts of different jobs. Um, Basically, you can break it down into four different types of jobs. The first is what she was doing, which is environmental work. If you're interested in protecting the environment, there's all sorts of environmental science jobs out there. You can stay in the state of Tennessee, or you can move to some other part of the country, or you can go around the world. Obviously, if you go to certain parts of the world, you're going to need to learn foreign languages. And then environmental work is really rewarding. We want to protect the environment so that the public is protected from pollution. And you can do that working for the government, working for the EPA or Tennessee state government or Kentucky state government or wherever you're working to enforce environmental law. Or you could work for a company. Companies need environmental scientists to make sure that they're in compliance with environmental laws. Let's say you're working for GE, for example. You make sure that GE is in compliance with the environmental laws. The second type of geology job involves natural resource extraction. That means getting oil, natural gas, coal, clean water, minerals out of the earth. We need to have um, natural resources, minerals, to manufacture every product you might have, including that laptop you're looking at right now or your cell phone. It involves hundreds of different minerals to make a cell phone or to make a lamp or a television. Um, we need a manufacturing base in our country. We need to make things in America again. We can't compete with the rest of the world if we don't have access to these natural resources. So the mining industry needs people. We need oil, natural gas, and coal so we don't have to import this from other countries and increase our national deficit. And we keep the jobs in this country. And if you want to go outside of the United States, there's lots of jobs available. If you want to travel, if you always wanted to see the world, geology is a good job. Geology is basically for people who like the outdoors. I love the outdoors. I wouldn't want to be a suit and tie guy going into an office all the time. I like to be outdoors. Geology attracts people who want to travel and be outdoors and make a good living. A third type of geology job involves, she was mentioning natural disasters, earthquakes, volcanoes, flooding. We're heavily involved in predicting when these natural disasters are going to occur, what we do after the natural disaster occurs, and how we clean it up. So that's another field that you can go into. The fourth field you can go to in geology is into education. You could use your geology to, let's say you had a bachelor's degree. You can use it to teach K through 12. It'll make you more valuable to elementary, um, middle schools, and high schools if you have a background in geology. Or you can go on to your master's or PhD and teach at the college level. Or you could work for museums. Museums need a lot of geologists to set up their exhibits. So those are the sorts of things that geologists do. Um, if you are interested in going into geology, you get an A in this class, I'll help you. I will write you a letter of recommendation. I'll introduce you to people at UT if you want to go there. I have a lot of friends at UT. Let me just show you some of the things that we've done working with UT. I'm going to show you some photographs here. These two guys here are going into geology. Very smart guys. And we went out to Tremont to do some geology work. Let me show you some other pictures here. This is also from Tremont. All these young people here she's a Pellissippi professor. All the rest of these they're going to be geologists. They're going to make a decent living. And we have good schools in Tennessee. We have UT, ETSU, MTSU, or you could go out of state if you want to. Penn State is a good school in geology. That's where I went. Southern Cal. It depends on where you want to go. So there's me. Look how happy I am. I'm looking at a pile of dirt. Man, I'm happy. And we were actually looking at these different soil samples to figure out what sort of organic matter was in there. But soil is another thing that geologists study. We want to make sure that soil is fertile so we can grow things in it. The geologists are interested in soil science, which is called agronomy. Agronmy, also agronomy. So if you're interested in agricultural science, geology is going to be of use to you as well. And here's some more students, and we were very happy to do all this work with all these different people. A lot of them are going to be great geologists. Anyway, I'm happy to have been of service to helping these people get started in their careers, and I'll help you if you want me to. Now let's start getting into chapter 1. So this is from your textbook. First thing we want to do in chapter 1 is understand what science is and how it works. So, what is science? Well, let's talk a little bit about the scientific method. And the scientific method is a powerful tool that we have used to develop everything you have around you that makes life easier. Electricity, the internet, computers, cell phones, television. If you go further back into the past, radios and steam engines. It's, what scientists do is they study things that are of interest to the public. And what engineers do is they apply science to developing products that can be used by the public, or buildings, or anything that might be manufactured. So engineering is sort of an application of science. But you need that basic scientific knowledge in order for the engineers to have the tools that they need to accomplish the goals that they have. And science is based on, let me write it down for you here. I'm going to make a new note here on my computer, so I can write things down. It's based on a hypothesis. What is a hypothesis? Think about it for a moment. What did your high school teacher tell you about what is a hypothesis? A hypothesis is, you might have heard it be called an educated guess, but what a hypothesis is it is an educated guess as to why something is the way it is. And so the first thing you need to do as a scientist is you need to figure out, what problem are you trying to solve? What are you trying to learn? What are you trying to learn about? So you have to ask yourself a question, and that question has to be important to the scientific community. It has to be something that people are interested in, and they're willing to pay money for you to do. Well, once you find that question, let's say you had a question about, just out of the blue, why are there less mountain lions, or why are there no mountain lions left in Anderson County, Tennessee? And what would be some educated guesses in your mind as to why there are no longer any mountain lions in Anderson County? You know, one hypothesis might be that they were hunted out. It's due to hunting. One might be it's due to disease. Another might be it's due to habitat encroachment, people moving in, and there being no space left for the mountain lions. Your job as a scientist is not to say, oh, it's due to hunting or it's due to disease. You're not there to prove a point. You are there to be honest and to look at the data. And you have to set up a plan to test your hypothesis. So hypotheses need to be tested. They need to be testable. If you can't test a hypothesis, you're not using the scientific method. That's why when some people talk about the origin of the universe, we're going to learn in this class that scientists believe that the universe is 13.7 billion years old. And we have a reason for believing that. But one idea might be that it was created by a big bang. We can't test that. So a lot of people think that that's not really science. But when you're talking about big things like the formation of the universe or the Earth, there are ways of indirectly testing it, and so it can still be considered science. But for most scientific studies, you have to have something that is replicable. That means once you publish it in a paper, and it has to be peer reviewed, that means some of the smartest people on the planet are going to be looking at what you did. They have to be able to reproduce your observations or your experiment. If it's not reproducible, we don't consider it to be science. It's a very rigorous thing, science. It involves um, identifying a problem that we're interested in, coming up with a hypothesis, an educated guess, and then being able to test it. So, going back to our mountain lion example for Anderson County, let's say our hypothesis is that they died out because of hunting. Well, you're not there to prove that they died out from hunting or they didn't die out from hunting. You're just there to see where does the data take you. So one way you could tackle that problem is you could look at the records of how many mountain lions were killed by hunting over the last 200 years, or as far back as you can go, and then you have another set of data you can look at. How many mountain lions were thought to be in Anderson County in 1843, in 1859, in 1912, in 1943, in 1972, and you see, is there a statistical correlation between the reduction in mountain lion population and hunting? And if there's a statistical correlation, then you can do one of two things to that hypothesis after you test it. There's only two things you can do with a hypothesis. You can reject the hypothesis, throw it in the garbage, or you can fail to reject. It's important to mention, ladies and gentlemen, that you cannot accept a hypothesis. You can never accept a hypothesis. The best you can do is fail to reject. So if you see a statistical correlation between the amount of mountain lions in Anderson County, Tennessee, and the amount of mountain lions killed by hunters, you can fail to reject. That means it's still possible. Then you have to look at some other data, and and you keep testing this hypothesis. It's important to note you never accept a hypothesis. You just fail to reject. And when you fail to reject many, many times, then you could say, well, maybe that is the reason why. It looks like our data indicates that that's the reason why mountain lions have been reduced in numbers. It's due to hunting. On the other hand, if you don't see a statistical correlation, you have to throw it away. You have to say, no, it's not hunting. It's something else. It's disease or habitat encroachment or some other factor. If a hypothesis stands the test of time, so that over decades we've tested and tested and tested and tested, and we still fail to reject, then we move to something even stronger in science. And that's called a theory. So a theory, like the theory of plate tectonics and the theory of biological evolution, those are things that have stood the test of time, where they've been tested over and over and over again. We keep failing to reject. So bottom line is, a theory is something much more solid in the scientist's eyes. It is something that seems to work, and we can use it a lot more freely in understanding things, the natural world around us. We'll be talking about theories like plate tectonics and biological evolution, for example. And then if a theory is tested for a large amount of time, for example, centuries, then it could become a scientific law, which is even more solid than the theory. the law of gravity has never been violated. It seems to work always, not only on our planet but throughout the universe. So this is the strongest that we can get. It's a law, scientific law. The laws of thermodynamics. You're going to learn about that when you take chemistry, which govern heat transfer. The three laws of thermodynamics. Those seem to work always. They always work. We can't. We thousands, tens of thousands of studies, and a law is about as is the strongest we can get in science, scientific law. And the more solid a scientific idea is, going from hypothesis to theory to law, the closer it gets to something which we call probabilistic fact. Probabilistic fact. And a probabilistic fact basically means probable. I think I can spell by now. Probabilistic fact means that based on everything we know, this is as close to a fact as we can get. But we never in science have a true fact. It's the emperor has no clothes thing. Sometimes we can believe in something so much that we fail to test. You can't be like that in science. You always have to be able to keep an open mind, to think in your back of the mind, well, the whole world believes in this, but I still, if I see information that contradicts a law, I have to go with that as well. And so that just shows you the power of science, because it's testable, and it has to go through publication. That means you have to write a paper about it, and you have to describe how you came up with your results. People from all around the world, in all around the United States, all Canada, they're going to look at that paper, and they're going to ask themselves, did you test that hypothesis correctly? Were your observations make sense? And that's what we call peer review. PEER review. When these scientists look over your paper and they determine whether or not your conclusions make sense, whether or not your data is reliable. You can't pass things by, people. You can't lie. You can't fudge the data, because it has to be reproducible. If you are a dishonest scientist and you make up fake data or to for your own personal gain, or you're going to get caught, because there are some very smart people, very smart men and women, who are going to check on your experimental method and your results. And that's why science is so powerful. It's based on honesty. It's based on a rigorous methodology. So you're going to see all kinds of things on the internet that are not science. It's based on like the Loch Ness Monster. There is no way that the Loch Ness Monster lives in Loch Ness. I'll tell you that. Because that is a creature that lived more than 65 million years ago and is 30 feet long and 20 feet tall. You can't hide in a lake like that. They did. So you're going to see stuff, crazy things on the internet, like the Earth being flat, or that the astronauts never landed on the moon. That's fake science. That's not science. It's based on people who are not really using the scientific method. Scientific method things. We're not here to cover up anything. Scientists aren't. You can't cover it up. People are going to find out. So That's what the scientific method's about. To give you an idea of how the scientific method works, let's talk about this man here. His name is Alfred Wegener. Who is Alfred Wegener? Well, you're going to get to know this man. Let's talk about him. Alfred Wegener. And why am I not calling him Wegener? Because he's German, and in the German language, W is pronounced V. Ich verstehe ein bisschen Deutsch. I can understand some German. And I went to Berlin, and I went to the Alfred Wegener Museum. And learned a lot about this man. He's the man who got me interested in science in the first place. And he changed the world by using the scientific method. Who is he? Well, in 1912, he was looking at maps of the world, and he noticed something that I noticed when I was a kid, which was he noticed that the continents of the world fit together like pieces of a jigsaw puzzle. Have you ever noticed that? A lot of people have noticed that. If you take the continents of the world, they fit together like pieces of a jigsaw puzzle. And Wegener said the reason why the continents of the world fit together like pieces of a jigsaw puzzle is because they were once together. And if the continents are no longer once together, are they? So they must have drifted apart to their present day positions. What Wegener said was quite profound. What he's saying is that the continents can move. Now, this has now become a scientific theory because all of the evidence indicates that the continents do move. We have GPS now. We can measure the movement of the continents. For example, we know that the distance between Paris, France, and New York City is increasing by 2.5 centimeters a year, about 1 inch a year. So which ocean is becoming wider? The Atlantic or the Pacific? The Atlantic Ocean must be becoming wider if we're moving away from Europe. Europe is moving closer to Japan, so that the distance between Los Angeles and Tokyo is decreasing by 3 centimeters a year. We can actually measure the movement of the continents because of this important theory from Herr Wegener that was introduced back in 1912. First as a hypothesis. Now it's stood the test of time. All the evidence indicates that Wegener's idea was correct, but he had to go through pure hell to overcome the ideas that people used to have before 1912. The people used to believe in another theory called Permanism. What in God's name is Permanism? Well, let's take a look. Permanism was the idea that people used to have that the continents have always been in the position that they are today. They haven't moved an inch. Wegener changed that. but it took decades and two world wars and all of the information that was gathered during the Great War called World War One and World War Two, the interwar years, going up all the way here to the year 2020. All the information poured in from various scientists around the world, and they all supported his theory. This is the most important scientific theory in geology, plate tectonics. And the next chapter is about plate tectonic theory. I highly recommend that you really study this theory because once you understand plate tectonics, you're going to understand why the Earth the way it is. Why? How did the Appalachian Mountains form? How did the Rocky Mountains form? You're going to understand why the mountains that we have here in Tennessee are made up of the same rocks as those in England and Scotland and Norway. You're going to understand the distribution of fossils around the world, where oil and natural gas and minerals are found can be explained by plate tectonics, where we have earthquakes and volcanoes. For example, we have volcanoes along the edges of the Pacific Ocean. Have you ever heard of the term the Ring of Fire? It burns, burns, burns around the edges of the Pacific Ocean. That's called the Ring of Fire. Anyway, another scientific theory that we really want to learn about is Charles Darwin's theory of evolution. I'll tell you right now, I believe in evolution. And it's the basis of modern day biology. And I don't think it means there's not a creator. I believe that, in my personal opinion, that evolution does not prove or disprove the existence of a creator. I happen to be a Christian, but it simply states evolution means that species change. It doesn't say there's a creator or not a creator. Species change, and only the fittest survive, and the fittest pass on their traits to the next generation. That's common sense. For example, in the distant past, we had giraffes with long necks, short necks, and medium length necks. The leaves were high up on the trees due to drought. Who died? Well, the only ones who could survive were the ones who could reach the leaves, the ones with the long necks. That's what led to giraffes developing long necks. If you have what it takes to survive and you attract the opposite sex and you produce fertile offspring, your DNA gets passed on. It's the basis of modern day medicine. When we develop antibiotics such as penicillin, penicillin used to be 99% effective in killing various diseases. Now it's less than 50% effective. Why? Well, think about it. If you have 1 million bacteria and 900,000 of them, 990,000 of them will get killed by the penicillin, who survives? Only those bacteria with a resistance to penicillin. So the next generation is going to develop a resistance to the antibiotics. That's why we have to keep developing new antibiotics, because bacteria develop a resistance to our antibiotics. DDT back in the 60s and 70s used to kill 99% of mosquitoes. Only those mosquitoes who have a resistance to DDT are going to survive. And therefore their traits are going to get passed on. That's what evolution's about. It is a solid theory. It's a basis of modern day biology and modern medicine. It doesn't tell you that there's not a creator. Many Christians, for example, believe that God could have created evolution. He would have wanted his creations to survive that we're not giving God credit enough. It doesn't prove that there's a creator either. It simply states that favorable traits get passed on because they were an advantage. I don't know any of you people, maybe one person I know in this class from a previous class, but whoever you are listening to this video, you are who you are because your ancestors had what it took to survive in the world that they lived in. Geologists don't think about things like most people. I think about things that happened 500,000 years ago, 100,000 years ago, a billion years ago. Well, let's just go back 20,000 years ago in your family line. There are thousands of your ancestors who were living during the Ice Age then. They had what it took to survive during the Ice Age, and therefore their traits were passed on ultimately to you. That's what evolution's about. So those are the two main scientific theories that we're going to focus on: plate tectonic theory and biological evolution. It's important to note that Charles Darwin himself was not an atheist. He believed in a creator. Um, Something that a lot of people don't know. Anyway, the scientific method is a very powerful tool, and it has led to almost every advancement in mankind over centuries. And another example that we could look at is going way back in time. People used to believe in what we call a geocentric view of the universe. Let me show you what that means. So, going back to the ancient Greeks, all the way up to the year 1432, people used to believe in a geocentric model for the universe. And the geocentric model of the universe can be shown by this picture here. Geo means earth, centric means center. And the ancient Greeks, starting with Aristotle, used to believe that the earth was at the center of the universe, and that the moon and the other planets and the sun revolved around the earth. That's what people used to believe in. They believed that the stars, picture it here, were embedded in a crystalline sphere, and they called that the celestial sphere. This model for the universe dominated scientific thought until the year 1432. And the year 1432, a famous man came along by the name of Nicholas Copernicus, who changed the world. Who is Copernicus? Well, Copernicus was the first person to come up with another model called the heliocentric view of the universe. Helio in Latin means sun. So Copernicus, back in those days, we didn't have telescopes. We used something called pointers, which they had let me show you what a pointer is here. Let's see. So there's Nicholas Copernicus. So before we developed the telescopes, we didn't develop telescopes for um, um, astronomy until Galileo. This is during medieval times. Can't even spell. Anyway, these devices. Let me Okay, I got there's. Let me show you some pointers here. Pointers, astronomy, Tycho Brahe. This is what a pointer is. And back in the old days, before Galileo, we're talking about the 1600s and 1500s, 1400s. They used these devices. They would point at the stars, and they had all these dials that they could rotate this in three different directions. They would point to the star they were interested in, and then would move these dials as the star moved to track the movement of celestial bodies through the night sky. And um, so Copernicus used his pointers, and he found out, wow, my astronomical measurements don't measure up with the theory of the geocentric view of the universe. And as a good scientist, he did what he was supposed to do. His data showed that the sun was not at the center of the universe. I'm sorry, the earth was not at the center of the universe. He said the sun was, and that the earth is just another planet that revolves around the sun. And so he was the first one to figure that out, that the earth is not at the center of, it's the sun. Now, obviously, he did not know about the universe and galaxies and all the things we're going to be talking about, but he did figure out that the earth is just another planet that revolves around the sun. That's how the scientific method works. When you get data that goes against long held theories, you have to go with it. And going from the geocentric view to the heliocentric view changed the way we look at the world. I'm going to take a break now to feed my dog and eat lunch. But I'll make another video here soon.